The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to today's Tech Talk on commissioning fan arrays and direct drive fan applications. My name is Sherry Adams, and I will be the moderator for today's session. Please note that throughout the Tech Talk, all phone lines will be muted. This will minimize any background noise or feedback that could distract from the presentation. When you first joined the Tech Talk, an attendee control panel appeared on the right side of your desktop. On the left side of this control panel is a small tab with an arrow icon at the top. Pressing this icon allows you to minimize and maximize the control panel. When maximized, you can use the control panel to submit questions. We'll be gathering your questions throughout the Tech Talk, and we'll leave a little time at the end for Q&A. If you have any questions related to a particular slide, please include the number of that slide in your questions. A PDF of the slides from this presentation will be sent out electronically to all those who register for today's Tech Talk. We will also be recording it, and it will be available on our website under the resource section. There is a new password to access the Tech Talks, and it will be emailed out to everyone after the presentation. Today's presenter is Brian Mendy. Brian is an engineer and the commissioning authority in charge of Central Texas for Bath Commissioning Group. He is headquartered out of Corpus Christi's office and is responsible for the design and commissioning of mechanical systems for institutional, military, and industrial applications. He has designed and commissioned systems that include hospitals, research laboratories, large distributed steam, hot and chilled water systems, municipal water systems, HVAC systems, plumbing systems, industrial piping system, and fire protection detection systems. So Brian, I will send the presentation to you.
Okay, thank you very much, Sherry. I'm Brian Mendy, like she said, and I am with the Bath Commissioning in Corpus Christi. Today, I'm giving a presentation on commissioning fan arrays, and we're going to talk a lot about the direct drive fan applications. We'll go back to this first thing here. It says delivered by members for members. I am a member of BCXA, and I think as a group that we need to work together to try and get as many members as possible to join up, because the knowledge that we can share can increase our industry tremendously, okay? Now, the things that I'm going to talk about here are not a direct reflection of what BCXA does, or in other words, I don't want to say something here that you might think that someone from BCXA is saying that you should be doing. In reality, this is just by me as a member to you of kind of the way that I approach direct drives and fan array applications. Come on. Today we're talking a little bit about fan arrays, some direct drive fans and why you would use them and what applications. To discuss that, we have to talk a bit about the basic VFD operation and variable torque applications is what we have here. I'm going to give some examples, some design reviews, and some note reviews of fan arrays that I have found issues with or possible issues with. And then I'm going to go over how I approach a fan array and how I set up the drive when I'm working as commissioning agent on a fan array. I'm very much a hands-on commissioning agent, so a lot of times I don't have mechanical contractors, control contractors with me when I'm doing the work. Some people are not being in that situation, but you still have the same kind of setup to go over. Why would you use a fan array? Well, some people tell you that they're energy efficient, and that's not necessarily true. And we'll get into that a little bit later in the slideshow, show you why it's not that efficient sometimes. Quieter operation, I would agree with that. They can be quieter than a very large fan. Redundancy seems like the big thing that all the owners want to go for. They want to see a 9-fan array where if 2 of the fans fail, they still have some kind of air conditioning in there. I have an example later on in here. We talk about the types of fan arrays, and I'll show an exact example from the National Institute of Health that we applied for redundancy. Maintenance is another big issue, and not just the maintenance with the no belts and shivs. You also reduce the drive losses. So the efficiency increases in that aspect, and that you don't have to have a belt and then the shivs and have that drive loss and that friction. You're just using just the motor and the fan. So you do get some energy efficiency added out of that, on top of having no maintenance of the belts. You know, that's a big one when they're annual maintenance and they got to check the belt, et cetera, et cetera. The air handlers are typically smaller in size. If you think of a 100 horsepower fan section, how big it is for a single fan, and if you think if you had a 9, 10 horsepower smaller fans, it actually squeezes into a shorter cabinet. Sometimes the cabinet's taller, but could be a shorter cabinet. But at that kind of CFM, you can imagine how big the coil is. Top of different types of fan array applications. This is a setup in which you have, on the right-hand side, you see over here, this is a 4-fan fan wall. And they have one drive feeding the 4 fans. Now this happens that this drive here is set at the horsepower equal to the sum of all these motors in here. Now that kind of iffy saying there because you have startup, various other things that go into the size of this drive, but essentially that's what you're doing. Now the drive usually acts as an overload for your fans and your motors on your fans, I should say. Well, since we have one drive and we're feeding 4 fans, we have to have separate overloads. So here in the picture on the bottom right, I took a picture of the inside of a cabinet here. This is the line coming. This is the line coming in to the disconnect right here. Where we can see that, and then you have the 4 overloads down below it. So you have overload for fan 1, fan 2, fan 3, and fan 4. These overloads are independently set based upon the overload of each individual motor on the fan. So the drive, in effect, isn't going to act as an overload limiting device. In other words, when that drive is getting, if there's only 2 fans running at a time, the drive is set to like trip out at the horsepower of, just say, the 100 horsepower and not the 50 horsepower. So the drive will not protect those motors if they start to overload. It's a natural thing. The next setup is the one that I've seen on the National Institute of Health. No, this is a drive, I'm sorry. This is a drive setup where you can actually have independent VFDs for each fan motor. In this case, we have 4 fans, and each fan has a VFD associated with it. This is probably the most expensive, sweetest setup you can have, because each one of these drives now acts as an overload protecting device on that motor, and on top of that, it's acting as a starter. So you have all 4 of these drives that can actually ramp up each individual fans, or even sometimes you can look at the energy savings and you can say, well, I can save more energy only operating 3 fans instead of running 4 fans at a time. And in that case, you have a smart program, which some vendors have, that can go in there and actually figure out which drive and which motor needs to drop out. Because we'll talk a little bit about energy efficiency. You'll see what happens when we start getting motors part loaded, and we start getting VFDs part loaded, about what really happens to the efficiency of the electrical setup. Now, the problem with this is this costs the most. And of all the fan arrays I've done, I've only seen this done at one time. And this is the job right here you're looking at. The other setup is kind of a combination of the two. This is where you can have, this is a 4-fan wall, in which you have 2 fans on one drive, and you have 2 fans on another drive. This is an application with the National Institute of Health, in which they wanted to have redundant fans. And we convinced them that we could use this setup to show as redundant. And we had to come back in and calculate how each drive worked with every 2 sets of fans, such that if one drive failed, then the other 2 fans could make up the difference enough to keep the space safe. And then, or if one fan failed, then we could also wrap up the other fan to maintain the differential set point or flow rates that we're looking for. This is a medium cost. This costs you a bit more. You think about it, you're going to have overloads on each one of the motors, and then you have to have the 2 drives. So all you're really saving is the cost of drive. We could come in here on this one and put 4 drives on it, and we probably could have done the same thing, sizing up the fans. You'll see that sometimes on hospitals where they want to do a 2N redundancy or N+1, and you'll just see that drive setup. Now, I should say the fan array setup. I kind of want to make sure everybody understands that this is a very quick presentation. There's a lot more detail. There's a lot more different type of systems that are available out there to use, and that I'm just kind of giving a really brief overview of the things that I've seen I think are important in Tech Talk that we can share together and work, and kind of get excited about when you see stuff like this. It's really fascinating, and it's also fun to work on these things. I'll talk a little about VFDs because we can't really talk about direct drives until we talk about VFDs. This is I think I got out of NEMA so that you can kind of see how a pulse width modulation drive works. What it does is it modulates the voltage on and off to create a different wave. So we might have on the line side, for instance, 460 volts. That would be coming from the panel to the VFD. Now, when the motor starts operating at 30 hertz, the wave is actually turned on and off. And so that pulse width really kind of tricks the drive on the load side to looking at 230 volts at a half speed. Now, I say that, but in reality it's different just because they're non-linear. So just as for understanding sake, just remember that when this motor is running at half speed, it's running at a very much lower amount of voltage. And that is sometimes is what bites you in the butt on these systems, is that the vendors will come out and they want to minimize the cost of the thing, but it can be detriment to what your owner wants to have done with the system. When VFDs speed up, they're sized to go to 60 hertz. And so when you get to 60 hertz, as you can see from this graph here, that our percentage horsepower and torque increases. We have a constant torque until we get to 60 hertz. And once we get past 60 hertz, we maintain constant horsepower and we start dropping torque. I think when you get the PowerPoint presentation of this in the PDF, read the bottom of this thing a little bit closer and try to get a handle. I'd recommend trying to get a handle on all this. It took me a while to understand it, but for some people this is like, yeah, it makes total sense. I know this for 20 years. But we'll go on. Now this is where, to me, I think this is where it gets a little tricky with VFDs and direct drives. So I said earlier about it, this stuff really energy efficient. Well, you can see that this is the energy efficiency standard, the top one, the minimum for standard premium. As you can see, is that a 4-pole motor, which is a nominal 1800 RPM motor, is probably the most efficient motor made. But as you can see, that in this case, a 1 horsepower motor is not as efficient as a 4 horsepower motor by quite a bit. Then we start taking into account the efficiency of the drive. This is your drive efficiency and the horsepower. As you can see that when it gets out to the end and the VFD is actually going full output, it runs the most efficient. Is when it starts coming back into here, let's say at 25%, that's running at 15 hertz, it loses quite a bit of efficiency. And then also we can come back over here and we can look at fan classes and see how they operate. So we have fan speed and RPMs over here on the right, and as you can see that the bigger the fan, the more static and total efficiency we gain. So we actually have a better performing fan. So when I talked about energy efficiency sometimes, well, I can tell you that 4 1 horsepower motors with 18-inch fan is probably not as efficient as a 2 horsepowers with a 22-inch fan, just because of the nature of how all these come together. This is something that I would recommend that you look at closely, and when you're figuring these things out, this would tell you the efficiency. So if somebody tells you it's always more efficient, they're not always right. It's not always more efficient application. When I look at these and I'm looking at design practices, and we go back to the VFD idea where the motor, the voltage is actually lower at slower speeds. I mean, it's actually lower, so to get the same brake horsepower, you have to increase the amperage. So that being said, is like, for instance, I'll give an example. Let's say you have a 10 horsepower motor that's pulling 9 brake horsepower, and it's operating at 1,140 RPM. And the motor that's put inside of it is 1150 RPM motor. And this motor is direct driven, and it has a variable frequency drive. Now that motor burns up, and the guy in the shop says, well, they don't have a 1150 RPM motor, but they have a 1750 RPM motor that's 10 horsepower, okay? So he thinks that he can go down there and he's going to grab, because it's 10 horsepower, and take it off the shelf and put it into this fan and reconnect it to the fan. And then he said he's using a variable speed drive to operate it at 1150. Well, the problem is that fan, that motor wants to draw, that fan requires 9 brake horsepower at 1150 RPM, or 1140. But that motor is now going to be operating at about 66% speed. Well, at 66% speed, the voltage is so low that the amperage has got to surge very high to create the same amount of brake horsepower. Brake horsepower is in this first equation on top. So what will happen in that case is the moment he starts it and he starts to dial it back, that motor will never work. It'll always overload because that fan requires too much brake horsepower. He's trying to slow the motor down with the drive. It will never happen. Now, if you had a belt drive, you could just reshiv it. But in this case, we have a direct drive. So I have a kind of rule of thumb that I use when I look at the submittals and design requirements. And it is that when the motor overloads, when the brake horsepower divided by the nameplate horsepower is greater than the ratio of the speeds on a one-to-one basis. So if I had, for instance, the 9 divided by the 10, in this case of the 9 horsepower and the 10 horsepower, and the speed was 1140 divided by 1750, well, the ratio is greater than the motor speed divided by the motor speed at load and then the normal motor speed, the NP motor speed. So at that point, it overloads, and I've seen it happen multiple times. Your vendors are not perfect. The vendors that supply these are not perfect. They will do crazy things sometimes. Let me go ahead and see if I have anything going on. Okay. This slide is an actual submittal review that I did. And in this case, it was a Cook centrifugal blower for a laboratory. It's actually a pretty good size fellow, too. Let me see. It's a 10,600 CFM blower running at about 3.4 inches of external on it. And what they did is they submitted it as a belt drive, and the engineer came back and said, no, we want to have a direct drive. So the vendor just went there and said, okay, direct drive, and left everything exactly the same. And I did an analysis real quick. On the right-hand side, you can see my analysis. It says that there's 1304 RPM, and the motor is actually 1725. And that our brake horsepower of a 10 horsepower, he started off with 7.96. I should say, with his horsepower, his brake, my eyes are bad. Yeah, 7.98 or something. And he put a 10 horsepower in it. Well, the problem is that at that reduced speed, that would be about 45 hertz because it was spinning so slow, and the voltage would drop so far down that the motor would overload. And so we caught this before we'd ordered it, and those fans end up becoming belt driven. It's kind of a shame. He should have put 1150 RPM motor and then oversped it above 60 hertz, which is not uncommon. And we probably could have got away with it the way it was. The system was oversized to start with, as we know all the time. That happens, and we could have gotten away with a much better setup, but this is the way it went. This here is on the design review, and this is the current project I have right now. Looking at it, everything it looks like it's done by the vendor. So the vendor kind of put all this stuff together, particularly when it has 119.62 inches. You know, I mean, does that really make a difference? But, or, you know, max, there's crazy numbers in there for some reason. But if you look at air handler -0, AHU-0, I wrote on the bottom right there, is that the fan speed, the fan is at 16.5, and there's two of them, and the speed is 2,528 RPM. Now they're bringing a nominal horsepower motor, nominal speed motor of 1,800 RPM. So I looked at that, I said, you know, that motor is running at 84 hertz. Both of them are running 84 hertz to maintain that pressure and flow. And so I don't think the owner knows what they're looking at a lot of times. And I said, you know, this is not acceptable, because if one fan fails, the other fan isn't going to do anything. And probably because the pressure's dropped so much, it's going to overload immediately. So you don't have any redundancy in this case at all. What's going to happen is that one motor fails, the other motor, the pressure is going to drop, the other motor is going to spin out, it's going to go to the end of its curve, and that's it, particularly at 84 hertz. So I'd imagine that we've taken the drive and set the maximum hertz to 84. So in this case, I recommended, you know, why aren't we going with a little bit larger fan and getting those RPMs down a little bit? And then that way, when one motor fails, we can actually ramp the other one up and maybe limit the maximum frequency in order to maintain as much airflow as you possibly can. I look at air handler 1N is the one right next to it, and I said, okay, that one's running at 64 hertz, which is about 60 hertz, which is fine. I looked at the ratios of the horsepowers. So you have 16.5 is the brake. Each motor is 8.5. And that one looks like it's a pretty acceptable installation. And I think that looks good. And we should probably look at the fan curves and figure out what's going to happen when motor fails. On air handler 2 and 3 on the far right, one operates at 54 hertz, and the other one operates at 57 hertz. Now this is where we start looking at those voltages, okay? So let's look at his ratio of his horsepowers to the ratio of his speeds. And he has 20 horsepower brake on AHU 22 and also on AHU 3. Looks like we have our horsepower, looks like it's in a good thing, but we should probably go back and look at that and calculate it and make sure that if one fan fails, that we can actually ramp the other one up to a little while. I'll discuss how I like to ramp them up when I get them all set up to work. And these are just 2 fan arrays. I've worked on up to 9 fan arrays. I've seen 12s. I have never worked on an ECM array. I get to do one of those next month. I'm really looking forward to that. But this is all, again, just for AC motors, and we're talking load side VFD voltages and amperage that actually the motor actually sees. I'll go ahead and take a little break and see if Sherry has any questions for me, Sherry.
I was just going to say no, but it looks like one just came in. Let's see. It's a long one, so we'll go from here. Paul, a fan wall that fails actually starts to spin backwards. It can generate current back to the overload. VFD. Has this been an issue in past jobs you've worked on? And if so, what has been the solution other than monitoring excuse me, individual fan status and putting in shut-off dampers or brakes at the drive? And then he continues to say,
by the way, that's, go ahead.
Oh, I was just saying, then just to finish the information, he said, I have not seen this be specified on other jobs nor from the manufacturers that actually had power backfeed and blow and overload.
Yeah, I've never seen them blow the overload coming back, but the point is a very good question. Every fan wall that I've ever worked on, we've always had a means to shut off the flow to come back through it. We've done different things like looking at differential pressure to across the fan itself between the plenums, but that doesn't seem to work very well. But usually what we'll do is use a CT on each one of the overloads. We'll have a CT for each individual fan, and then when that fan fails, we have a motorized damper with a low leak damper on it, and we shut that one off. We do not typically like to see barometric type at all. They can get stuck open. And when we talk about testing here, you can have a problem with your maintenance personnel if they don't understand how to operate them, like by how to shut them down and how to restart them. And what I've seen before is the fan spinning backwards and somebody try to kick an overload back on, or try to kick something back on when that motor, the three-phase motor, is spinning the wrong direction. The application of brakes on the VFD is great, but if the VFD fails, it doesn't really do you much good. So I hope that answered the question. Any other questions before I continue?
No, that's it, Brian.
Okay, we're almost to the end of this presentation, but we're going to talk about commission fan arrays and how I do it. This is not necessarily how you can do it. This is just kind of the approach that I take, and I try to get the best setup for my clients and make them happy, and then the training is really tricky. So the first thing I try to figure out is, like, what is it my owner really wants? Do they want to have super redundancy? Is the idea to have an N+1, N+2, or 2N, or they really don't care just because of the fan wall fit in the room? And this is what the vendor said they should buy. This is what the engineer told them they should buy. So in a lot of ways, I try to find that action. What is the idea of how they really want to operate this, okay? Looking at energy efficiency, then that goes into individual drives. If you have that situation, that can be just all kinds of fun to commission, because it can be complex from the vendor. And a lot of times you have to say, okay, what are you saying, I guess, is true. But you really need to understand it. And then what I like to do is I want to find out what the fan can really operate. What is this fan and this fan wall system capable of? So the first thing I do is I try to understand the fan. So here's two separate projects I've had with different fans. Up on top is a train two-fan wall, which is operating at 66 hertz, and I look at the horsepower requirements in the system curve. So I try to find the maximum speed that the actual fan can operate at. On the right is a four-fan fan wall by Energy Labs. And as you can see, the maximum RPM of that fan, I have it kind of highlighted, is 1928. And so the fan's going to operate at 1920. That's the maximum frequency it can have. Like I misprinted at 28, so 25. Is about 66 hertz. And then the bottom line, you kind of see, I look over and I say, well, they say it's going to operate at 1750. So that tells me that the actual operating of this fan is going to be right around 58 hertz if, the big thing is if, that static pressure on the far right is correct. 31,000 CFM at 5.13 static pressure. I've never known an engineer to leave very much shortage in their static pressure. And I think that's where, if we can know the fan and we help our owner, we can actually help them save energy on these fan walls instead of trying to maintain this huge set point of 5.13. Imagine downstream it's probably supposed to be 1 inches, but that's the total static across the whole system. How I commission them is I look at the air handler, and I commission the air handler like I would commission any other air handler, all the way through chill water valves, chasing temperatures and stuff like that. I really want in a fan wall, I want to implement a differential pressure reset function. I want to change the differential pressure based upon where the terminal block is positioned. And that way I can actually dial back and I can take away the fat that the engineer built into it, because I don't want to have to put as much energy to moving that air and to maintaining the static pressure that I don't need to. And I think my client doesn't want that either. And then what I do is I'll go into all the different failure modes of the fans, and I record everything as I go through, and I purposely fail them. So first thing I do is I verify that each fan is failed and that it's reported. The next thing I do is I set all the terminal units to full cooling, and I record the static pressure requirement and the actual frequency of the drive. And I let that thing settle down, and hopefully that I have a reset function where that can really go down. So I can get that set point right where it needs to be, and I can say, okay, at full cooling, this is the only pressure I need to maintain downstream. Now we can talk about, pressure from the suction side of it with the filters and stuff like that. We're going to adjust it. I don't disagree with that. This is initial setup. I adjusted the drive to the frequency that it's supposed to be on the schedule, and I go into actually programming the drive to 60 hertz. And sometimes it can be above 60 hertz. And then what I'll do is I'll start failing the fans individually. And I'll fail, let's say in a 4-fan fan wall, I'll fail 1 fan. And the other 3 fans will ramp up and try to get to the set point. And then what I'll do is I'll record those settings. And then I'll look at the full, what the amperage is being drawn on the load side. I'm just saying the load side of the drive. And I'll look at that and I'll make a determination if I can go ahead and creep that frequency up. And sometimes I'll take it and I'll take the max frequency and change it from 62 maybe to 70 hertz. When I get to 70 hertz, I'll look at that amperage and see how close I'm getting to overloading the 3 motors. And then what I'll do is I'll trip off the second motor so that this 4-fan wall is running on 2 fans. And I'll look at that real close and make sure that the fans are on overloading condition at that maximum frequency that I set it at. So that if they have 2 fan fails, they're getting the maximum air out of that air handler that they can get. Big one, the last one is right there is, man, you got to tell that maintenance staff exactly what you're doing. Educate them on how direct drive fans are. What I like to do is I like to put the drive to show the load side and show them how the voltage and amperage react differently at part load than they do at full load. And I try to train them on that so they get an idea of what's happening with the drive. And then I start saying, if we go above 60 hertz, this is what happens. We're just spinning faster. And I try to get them through that whole idea about a 22-inch fan is at its most efficient at about 2,200 RPM instead of at the 1,800, which the motor is physically fixed at. So here's some of my scripts that I go through that I'll let you guys have. Here's one that I did on a small fan wall. I think you look at number 21, line 21, I placed them all in cooling, and I tripped one of the fans. And I maintained the 0.8 inches of what I needed. And the fans ran at 54 hertz without overloading, so I changed it from 54 to 55, okay? And then what I did from there is I failed another fan. So when 2 fans were failed, this would be script number 22. I went ahead and ramped up the drive to 60 hertz to make sure, because it wasn't overloading. And sure enough, I got right on the edge of it, 24.4 for the 2 motors running. And was not operating in the service factor. That's a put down there, not including service factor. Never operate a motor in the service factor range when you set it up. It's just not good practice. So what I did is I said at that point it was operating at peak performance of 24,000 CFM because these fans are way out the end of the curves. And I said, okay, I'm going to go back and look at the drive, and it passed the drive test. On the field, line 23, it says fail 3 fans. Actually, I have an issue with that. I think when I failed the third fan, the first fan overloaded, or no, that's not what happened. Something else happened. I didn't have a way to fail it without it shutting down the unit thing. Then what I do is I take it, I put everything back to its original operation and let it go. This here is a test of another 4-wall, which I got carried away with, where I failed 1, and then I failed 2 individually and 3 individually. I don't recommend making a really complicated script like this. It's just a lot of time for you. In reality, you just need to do arbitrarily on a 4-fan wall, fail any one, and then fail any of the other ones. You don't need to like fail 1 and see what happens, restart 1 and see what happens, fail 2 and see what happens, fan 2. You don't have to do that. Just do what you need to do with failing just 1 fan individually and another fan individually. You don't have to go back and, in other words, don't test every fan. I guess my guy in my room look at me funny, saying, "What are you saying?" In other words, don't fail fan 1 and with all 3 of them running, then restart fan 1, and then wait till it's running, then fail fan 2, so you have 3 running, and then restart 2, and then fail fan 3, and you still have 3 running. Don't do it that way. And also, when you restart these fans, it's very important that you physically turn off the machine, because as the noted question earlier, you might have some spinning back on your fan, and that when you try to reset that fan, it's spinning in the wrong direction. The surge of current will hit the overload and trip the overload. If not on the drive, it'll be on the motor overload. So when you do this test script, you physically need to, when you fail the 1 fan and you get your point, what you do is you turn the VFD off, let everything ramp down, reset your motor overload, and then restart the VFD. And you also need to train the staff on exactly how to start and stop these things. It's very important. If not, they're going to just sit and overload the motors, and eventually they're going to turn it all off and then put it in bypass and just run at 60 hertz. If they can, without overloading it. I guess this is my first presentation of this, and I hope you enjoyed it. I'm ready, open for questions and answers. I mean, I'll answer any questions that somebody might have.
Yeah, Brian, we have a couple that have come in. If there is only one VFD controlling the fan wall, what method do you use to fail individual fans?
I actually go back to the overload. So there should be an error handler. There'll be an overload cabinet. And what you can do is you open up that overload cabinet, and you can reach in there. It's not like there's a whole bunch of high wires in there. No, there's no open live wires. And I actually trip it at the overload. The overload uses a handheld. You trip it, and I'll go ahead and spin it and drop that 1 fan out of the loop. That's how I do it.
Okay. Next question is.
And then okay.
Sorry, go ahead.
No, just to follow up to that. Yeah, no, I want to go ahead and follow up to that, because when I do that, like I just said, I turn that overload off and the 1 fan fails. Before I turn that overload back on, I need to go over and, like I said earlier, turn off the drive, let everything ramp down, reset the overload, and then restart the drive. Okay.
And the next question is, if the voltage drops as the fan speed decreases below 60 HZ, what happens to the voltage as the fan speed increases above the 60 HZ?
Yeah, that says that line voltage. I think that's why you see the torque. There's a lot of good papers written on that. And to tell you I'm an expert at VFDs and how they work and all that would be foolish of me. But when you get to line voltage, that's all you have is line voltage. And I think after that, they use a different method to make it go above the 60 hertz than with pulse width. So do a little research on that. I'd recommend so you can better understand what's happening there. But it goes to line voltage. You can't get more line voltage. So a lot of times what you'll see is you can put the motor is rated at, let's say the motor is rated at 480 volts, 460 volts. This is typical, but our voltage coming into our building is, you're always going to say 480. A lot of times I like to take the drive and I like to put the drive and say that the motor is 480. And then that way I get a little bit of difference in the amperage that it's pushing out to it. So if you, let's say you're getting 470 volts from the system and you limit your motor to get to 460, then when you start increasing that speed, you want to get to that line voltage as high as possible. So I like to put that line voltage at like 480. If that makes sense what I'm saying. You can do a lot of research on this. This is a very, very brief discussion that I'm hoping to get everybody's brain kind of thinking and figuring out what's really happening with these voltages, amperages, and these motors that are now direct driving fans instead of using pulleys.
Okay, Brian, we've had a couple more if we've got time here. How do you typically see the ability SS fans individually via BAS, or do they typically not see the ability via BAS?
Repeat that one more time, Sherry.
How do you typically see the ability, it's S/S fans individually via BAS, or do they typically not see this ability via BAS? S meaning start stop. Sorry, I wasn't.
I guess you're saying.
How do you typically?
That's okay. I think the question is how often do I see like individual VFDs for the fans as compared to one VFD for all the fans? I mean, that's a question. I've only seen that one time with all VFDs. Every fan has its own VFD. But I think in a totally different subject, there's going to be ECM motors. And I think you're going to see ECM motors are going to start, really you're going to have individual different speeds to set them at so that you can actually start and stop them. I think you're going to find that in the future. That's the way that, everything's always getting more and more different. And it's a DC brushless motor. I mean, we can go to whatever RPM we want. So right now, I don't see it very often because it costs so much. But I think in the future, we'll be having this discussion about with ECM motors pretty soon.
Okay, and then on your examples, were there isolation dampers?
Yes, on every one of those, there is an isolation damper. It's kind of, I work for some clients that have money. Okay. So we will always insist that they'll have isolation dampers. So for instance, on this one had 4 isolation dampers on it. This one is not shown, but it was there. This one it was not shown, but it was there. It might be the way I cut the submittal, but yeah, they always have isolation dampers on them, and those are critical components because you can have problems with them. We try different ways to verify fan operation, and I don't like doing it from the drive. I'm just a keep it simple kind of guy, and I always want them just to put the CT on the overload. If I got power going to the fan, then I have to make the assumption that that fan is on. And a lot of times I also want to have on the motorized dampers, I don't like them grabbing, like I said earlier, is I also request that we have a feedback signal. So we have a open close. So we know when it's open. I guess that we got a limit switch. I want to know when that damper is open. So a lot of times, like when I do like a lab system, let's say I got 3 big green heck fans on the roof, what we'll do is it's almost like a fan array because it has different fans on one big plenum. So we'll run one, and then before the other fan starts, what we'll do is we're gonna draw a DP across the inlet damper into the exhaust fan and get it almost as negative to what the current plenum is, and then we'll start cracking that fan open. And that's a direct drive application also. So I like doing it that way too. Anyway, I didn't mean to go off on a tangent subject, but that's what I did.
Thank you, Brian. And it looks like we've run out of time. There might be a few questions that we didn't get to. And if you're open, I think on your last page of your slide, you have your email. If you're open to people emailing you with some direct questions that maybe didn't get covered or need more detail on.
Yeah, of course.
That would be great.
Oh, I'm sorry.
It's okay.
Well, let me go and go back.
Okay, we get it. Yeah, get it to that last page.
There it is right there.
There you go.
Well, thank you everybody for attending. I appreciate everybody attending and attending this webinar. I mean, this presentation from our group here in Texas, and hope you learned something. I hope it's something you can think about at least.
Well, we definitely appreciate your time and expertise, Brian. And just a quick reminder before we go, registration is open for this year's annual conference on September 25th, 26th, and 27th in Schaumburg, Illinois. So check out the website for some exciting things that will be happening, and we'll also be sending out some emails with more details. And one other announcement, if you all have a colleague that's been interested in membership, now is a great time to join because you get your membership for half the price. So anyway, thanks again, Brian. And on behalf of the BCA, I'd like to thank everyone for your participation today, and have a great day.